in the last lecture we studied a very important concept, what is called a Poynting vector of an electromagnetic wave. The Poynting vector tells you the density of the power flow at any location in the space. So, if you are having complex electric and magnetic field distribution, then one can ask at every location how much power is flowing because of the electric and magnetic fields, and essentially we can find what is called Poynting vector. So, the magnitude of the Poynting vector tells me the density of the power, that is watts per meter square, and the direction of the Poynting vector gives the direction in which the power is flowing. Using this concept, then we can now ask a question: if the electromagnetic wave is incident on a conducting surface, how much is the power loss in the conducting surface? We also discussed today an important concept, the surface current. We already discussed when we talked about the boundary conditions about the surface current. However, still it is not very clear what is the origin of the surface current. Do we really have surface current in practice? So, surface current essentially is the phenomena which is lying on the surface of any medium, and essentially this is the phenomena which is for an ideal conducting surface. Now, in practice we do not have ideal conductors, we have conductors which are having very high conductivity, but still the conductivity is finite. Then one can ask a question: does this surface current have any meaning in the practical systems, or it is just only a concept of abstractness? So, what we will do today, essentially we start from the volume current density inside a conductor. We know the concept of what is called the skin depth in the good conductor, and then from there we will essentially find out a current which is equivalent to the surface current, and then we will say even in practical system the concept of surface current is very useful in finding out how much loss takes place in the conducting surface. So, first we discuss about the surface current, and then we will go to the power loss in a conducting surface. One can ask a very simple question, that if you have a conducting surface, we have already said that if the normal to this conducting surface is given by n, and there is a magnetic field which is this on the conducting surface, that n cross h essentially gives me the direction of the linear current density, what is called the surface current. So, we have from here the n cross h, if we take like that. So, my finger should go from n to h, the direction of the current will be inverse. So, essentially there will be linear current which will be going inside the plane of the paper. This is the linear surface current density, that is what we talked when we talked about the boundary conditions. One can now ask a question: if the surface current is flowing here, what is the driving mechanism for this surface current? So, as I already said, this phenomena is a phenomena for infinite conductivity. So, if I take an ideal conductor, then maybe at some point of time instantaneously there was some electric field existed in this medium, and since it was a very short lived phenomena, we had electric and magnetic fields together. Now, for that momentary existence of the electric field would put the charges into motion, which will constitute this current, and since the conductivity is infinite, even if the electric field does not exist anymore, when the charges are put in motion, these charges will keep moving for infinite time, that means they will have current. So, when the conductivity is infinite, one may visualize this, that at some instant of time some electric field induce the motion to these charges now set in motion, and then they keep moving, which is essentially is the surface current, and then this is balanced by the magnetic field, and then n cross h essentially gives you the surface current density. So, basically there are two situations now, that you have a tangential component of electric field on the conducting surface which is 0, but there are no surface currents, and the tangential component of electric field is 0, but there is surface current. So in both the situations we have the tangential component of electric field is 0 for ideal conductor, but in one case we have surface current, in other case we may not have surface current. But if we have a surface current, then it must be balanced by the magnetic field. So if you have a magnetic field tangential to the conducting boundary, then and then only you will have surface current, otherwise we will not have surface current. Now this was the hypothetical situation when the surface current was truly flowing on the surface. What we now do is we just try to see if we take a good conductor, can we still make use of this concept of what is called surface current. It is very clear that if you have a conductivity which is not infinite, then because of the electric field there will be always a finite conduction current density inside the conductor. Also the skin depth is of finite width, that means this phenomena is no more a really truly surface phenomena, but when the electric field exists on the surface, essentially if I say this is the conductor, so on this side we have conductor, so let us say this is direction say x, let us say this direction is y, so which is coming out of the plane of the paper. If I put my fingers from x to y like that, then this is the direction which will be the z direction. So let us say this is my conducting medium which is for z greater than 0. So this side I have dielectric and this side I have conductor. So I have here conductor for z greater than 0. Now if I have some electric field at the surface of the conductor, now note here, since the conductivity is not infinite, this is not an ideal conductor, I have a conductivity for this conductor which is given by sigma. So the tangential component of electric field is not 0 now, because we are having the conductivity which is not infinite. So let us say I have a certain value of electric field for this in this direction, and that electric field essentially will exponentially die down. So if I say the value of the electric field in this direction was some E0, and the magnetic field which will be in the oriented in y direction, that will be H0. So we have electric field which is oriented in this direction, and then I have a magnetic field here which is oriented in y direction. So this is magnetic field. Then the electric field amplitude will decrease exponentially as the wave travels inside the conductor. So we are having an exponential variation inside this, which will be given as E0, which is the value of the electric field at the surface of the conductor, e to the power minus gamma z, where gamma is the propagation constant of this wave inside the conductor. So once we know the electric field value at the surface of the conductor, then this law is very well defined. Law is exponential law, and for once you know the conductivity of the medium and the frequency, this gamma is a parameter of this medium. So this quantity gamma, which is the propagation constant of this medium, that is square root, as we have seen earlier, j omega mu into sigma. If the conductivity is very large, that means this is a good conductor. So let us say, let me call this as a good conductor. By separating out the real and imaginary part, we know it gives you the attenuation constant and the phase constant. So this thing, as we have done earlier, this is also omega mu sigma upon 2 plus j times omega mu sigma upon 2. Now since this law is very well defined and the current now is flowing this way in the direction of the electric field, so we have a conduction current density which is sigma times E naught, which is varying exponentially as we go deeper inside the conductor. So what we can do, we can just take a thin sheet here which is having a depth of dz, and the conduction current which is density which is going to be in this will be sigma times E0 e to the power minus gamma z. So, if I ask now what is the current which is flowing in this sheet per unit area in the xy plane. So, if I take a area in this direction, the current is flowing this way. So, if I ask what is the current flowing in an area which is unit area in this xy plane, and I can find out the total current which is flowing under this surface of unit area in the direction which is x direction. So, essentially if I take the conduction current density and integrate over this depth, I essentially get the total current which is flowing under this surface xy, and if I take that surface as a unit surface, then I will get the current which is flowing under that area which is unit area. So, essentially we can write down in this region the conduction current density. So, we have conduction current density J, which will be a function of Z, and that will be equal to sigma times E at that location Z, which is nothing but equal to sigma E0 e to the power minus gamma Z, and since I am assuming that the electric field is oriented in x direction, I can take the direction of this conduction current density as the x direction. I can separate out the real and imaginary part of that to write alpha and beta. So, this I can also write as sigma E0 e to the power minus alpha z e to the power minus j beta z and unit vector x. So, now I know the conduction current density at this location Z. So, if I want to find out what is the current which is flowing in this slab of depth dz, that will be equal to the conduction current density multiplied by this, because I am taking the depth in this direction, in the y direction, which is equal to unity. So, the area of cross section, if I take, that will be dz into unity in that direction. So, the total current for unity depth in the y direction will be 1 into dz into the conduction current density. So, I have here now the current flowing in this small region. So, the current in the slab, this slab, that will be I of Z, that will be conduction current density J of Z multiplied by dz. So, substituting into this, this will be sigma E0 e to the power minus gamma z dz x direction. Then, as we mentioned, that now we want to find out what is the current which is flowing under the area which is unit area in this. That means, per unit length in the y direction, how much is the total current flowing under this surface. So, we integrate this in the z direction. So, we get the total current, and that current we call as the surface current. So, now note here, there is no true surface current, the current is actually flowing in this, in the depth, and actually it is theoretically extending up to infinity. However, since the conductivity is very large, we know that the skin depth is very small, that means this function is a very rapidly decreasing function. So, effectively this current will be confined to very close to the surface, but it is not truly confined to the surface. So, whatever we say that if we integrate this quantity in the z direction, we get that total current, and let us call that surface current to start with, and we will justify why we can still call it surface current. So, let us say if I integrate this, I get a quantity which we call as the surface current, let us say Js, and that will be from integrated over the entire depth, that means z going from 0 to infinity, this total current which is confined in that slab. So, I substitute here, which is sigma E0 e to the power minus gamma z dz to x direction. This integral is very simple. So, essentially this is equal to sigma upon minus gamma E0 e to the power minus gamma z 0 infinity into x direction. When z is equal to 0, this quantity is 1. When z is infinity, since gamma has a positive real part which is the attenuation constant, which is non-zero, in this case that quantity will be 0. So, essentially this surface current Js will be sigma upon gamma E0 x direction. Now, this quantity, as I mentioned, we are calling this surface current density. However, we have to justify completely that though this is not truly a surface phenomena, it has all the properties which the surface current has. And one of the quantity we know the surface current has is that the surface current is related to the magnetic field, which is tangential component of the magnetic field to the surface. Also, it should satisfy that relationship that n cross h should give you the magnetic field. So, in this case we have seen that n cross h, that should be equal to the surface current density. So, if this quantity whichever we are getting, this Js, if it should serve the purpose of surface current, it must be related to the magnetic field, and also it should be satisfying this condition that n cross h should be equal to the surface current. So, let us see, since I have the electric field on the surface which is E0 and the magnetic field is H0 on the surface here, if I go inside this, this is giving me a wave which is travelling inwards in the z direction, and this again is a transverse electromagnetic wave because this medium is unbound in this direction. So, your E0 and H0 must satisfy the relation that the ratio of the magnitudes of these E and H should be equal to the intrinsic impedance of the medium. So, if I calculate what is the intrinsic impedance of the medium for the good conductor, intrinsic impedance eta c is equal to square root of j omega mu divided by sigma. And the electric field and magnetic field are related, that magnetic field H naught is equal to E naught upon H naught is eta. So, H naught will be E naught upon eta. So, this quantity will be E naught upon eta c. Now, recall the gamma which we got is this quantity, square root of j omega mu sigma, that is gamma. So, eta c which I write here, this I can write as equal to square root of j omega mu sigma upon sigma square. But this quantity is square root of j omega mu sigma, that is nothing but gamma. So, this is equal to gamma upon sigma, square root of sigma square is sigma. So, this quantity eta c I can write as gamma upon sigma. So, that is equal to S0 will be equal to sigma E0 upon gamma. So, if I take magnitude of the magnetic field, that is what this quantity is, I will get the magnitude of the magnetic field, that is magnitude of electric field divided by the intrinsic impedance of the medium, which is eta c, which I can manipulate to get in this form. But this quantity is same as we have derived for the surface current, sigma upon gamma into E naught. So, that means magnitude of H naught is equal to the magnitude of the surface current. So, one relation which we wanted, that if this quantity is the surface current the way we have visualized, then it must be related to the magnetic field, and precisely that is what we see here, that magnitude of this surface current is related to the magnetic field. The second thing which we want is that the n cross H must be giving you the surface current direction. Now, again come here, in this case, since the electric field was in this direction, the conduction current density J was in that direction, and we have integrated this J over depth to get the surface current. So, the direction of surface current also is same as this, which is x direction. So, we have direction of surface current which is x oriented, we have magnetic field which is y oriented, and the unit normal to the conducting surface is this normal. That means the direction of the normal to the conducting surface is n is minus z. So, if I calculate n cross h, where h is oriented in y direction, I will get the orientation of h from here. So, n cross h will be minus z cross magnitude of the magnetic field, and it is oriented in y direction. So, this is y. So, that is equal to h0 into x direction. So, the n cross h, that gives me the direction which is x direction. We see that the surface current which we have got, that quantity is related to the magnetic field. That means this quantity which we have got here, which we called as surface current, in fact has all the properties which the surface current should have. So, n cross h gives me the surface current, and the magnitude of the surface current is same as the tangential component of magnetic field at the conducting surface. That is the reason in practice, though this current is not truly surface current, we use this as the surface current. Also, if the conductivity is very large, this current effectively will be confined to a very thin layer, that is the skin depth. And as we have seen earlier, if you go to the frequencies like few hundred megahertz, the skin depth typically lies in the range of about few tens of microns. So, essentially this is the current which is flowing in a very thin sheet close to the conductor. Also, it has the characteristic of the true surface current, that is, it is related to the magnetic field, and n cross h should give me the direction of the surface current. So, this quantity now can be used as a surface current for a good conductor, although in true sense there is no surface current for a good conductor. So, that is the reason in practice, although we do not have true surface current because the conductivity is always finite, we can make use of this quantity as surface current, and then we can do the further calculations by using this concept of surface current. Once we get this surface current, then we define an important parameter for this boundary, what is called the surface impedance, and this is very useful whenever we do the power calculations on the conducting surface. So let us define a parameter what is called the surface impedance, and that quantity is defined as Zs, that is equal to E tangential to the surface divided by the linear surface current density. Now let me remind you here that this quantity, which was the conduction current density, has units of amperes per meter square. We have integrated over one length, which is dz. So this has units of amperes per meter, which is the dimension of the surface current density, which is the linear surface current density. So here we have the unit for E, which is volts per meter. We have the linear surface current density, which is amperes per meter. So that gives me essentially volt divided by ampere, which is ohms. So this quantity Zs is some impedance, right, which is the surface phenomena because it is related to the surface current. So if I know the tangential component of electric field, then the surface current can be obtained from what is called the surface impedance or vice versa. Now if I substitute from this expression for Js and tangential component of electric field, which is E0, essentially we get this quantity Zs, that is equal to tangential component was E0, and the surface current which we got here, which is sigma E0 upon gamma. So this is sigma E0 upon gamma. So surface impedance is equal to gamma upon sigma. If I substitute for gamma, which is square root of j omega mu sigma upon sigma, I can take this sigma inside the square root sign. So that will be equal to square root of j omega mu upon sigma, and this quantity is nothing but the intrinsic impedance of the conductor. So this quantity is eta c. So for a good conductor, the intrinsic impedance of the medium is same as the surface impedance. However, we will see later that surface impedance concept essentially is used to calculate the power loss. So if I know the tangential component of the electric field, if I know the conductivity, I can calculate the intrinsic impedance of the medium, and that quantity will be same as the surface impedance. Once we have now this surface current density, then we can now ask how much is the power loss because of this current which is flowing in the surface of this conductor. So what we now try to do, we just take a surface and I ask, if I have a unit area on this surface, how much is the total power loss in this unit area of the conducting surface? As we already seen, since the current is flowing deep inside the conductor, essentially the power loss is not taking place only on the surface, the power loss is taking place all along the depth of the conductor. However, we will just ask what is the total loss which is taking, if I take the total loss inside the depth taken inside the conductor. So idea here is to find out, if I take a unit area on the conductor surface, So, if I take a area which is, let us say, a depth is dz and this is the unit area. So, this thing is unity, this thing is unity. So, on the surface of the conductor, I am asking if I take a thin layer which is parallel to the surface of the conductor, and since there is a finite conduction current density there, we can ask how much is the power loss in that thin sheet, and then if we integrate over the entire depth from the surface of the conductor, we will get the total power loss taken place in the unit area of that conductor. So, now let us find out what is the power loss in unit area of a conductor. The idea is very simple. Essentially, you find out what is the resistance of this slab, which is thin slab of thickness dz and area 1, and the current in this is flowing in this direction, which is J. So, from here I can find out what is the current which is flowing in this slab, and then from there I can find out what is the power loss, which is the I square R loss inside this slab, and then I integrate over the depth to get what is the total power lost in the conductor. So, since the conduction current density is J here and the current is flowing in this area, it sees the area of cross section, which is 1 into dz. So, the area of cross section for this conductor is area of cross section A is 1 into dz, that is dz, and the length of this conductor is unity, so that is equal to 1. The conductivity of this medium is sigma, so it has conductivity sigma. So, it has a resistivity which is 1 upon sigma, resistivity equal to 1 upon sigma. So, the resistance of this slab, if we calculate, we have a resistance which is equal to the resistivity multiplied by length divided by area of cross section. So, it is 1 upon sigma into 1 upon dz. So, 1 upon sigma dz. How much is the current flowing in this? That is J times the area of cross section, which is J multiplied by area of cross section, which is A. So, J times dz, that is the current which is flowing in this slab. So, I have the current equal to J times dz. So, the resistance of this slab is 1 upon sigma dz, and the current which is flowing in this is J times dz. Then I can calculate what is the power loss in this, which is the I square R loss. So, if I calculate now what is the ohmic loss in the slab, let us say that this thing is dW, and dW I am using because I am taking a thin sheet here. So, I am saying in this incremental slab how much is the power loss. So, let us say that quantity is dW. So, that is equal to this current square multiplied by the resistance. So, let us say half mod I square. So, let us say this current is I. So, this is mod I square into the resistance, which is say R, times R. I can substitute in this. So, J I substitute as sigma E 0 e to the power minus gamma z into dz. So, I can substitute this into this. So, this will be half mod of sigma is 0 e to the power minus gamma z, which I can expand to get e to the power minus alpha z e to the power minus j beta z dz square, and resistance is 1 upon sigma dz. This is 1 upon sigma dz. I can simplify this. So, this gives me half sigma square, 1 sigma will cancel. So, this is gives me sigma, this is mod E naught square and e to the power minus 2 alpha z into dz, 1 dz will cancel. So, this gives me dz. So, the power loss in this thin slab of depth dz is essentially given by this. Once we get that, then we can find out what is the total power loss under this area, unit area. So, we get now the total power loss under unit area on the surface which is W, which is nothing but integral of this from 0 to infinity. So, this is from 0 to infinity half sigma mod E 0 square e to the power minus 2 alpha z into dz. This integral again is very simple, the alpha is a positive quantity. So, this total power loss which we get is half sigma mod E 0 square e to the power minus 2 alpha z upon minus 2 alpha 0 to infinity. And since alpha is a positive quantity, when z is infinity this quantity is 0, when z is 0 this quantity is 1. So, this essentially gives you half sigma upon 2 alpha into mod E naught square. So, we got now the power loss for unit area of the conducting surface, and now it is a matter of only doing some algebraic manipulation to simplify for this term, which is sigma upon alpha. So, if I substitute for alpha, as we have seen earlier, the propagation constant gamma is given by this. So, this quantity is alpha and this quantity is beta. So, I can substitute in terms of alpha here in this, and I will get that is equal to half sigma upon 2 times square root of omega mu sigma upon 2 into E naught square. which I can combine in this. So, this thing, note here that alpha is this quantity, but mod of gamma is square root of omega mu epsilon. So, essentially this thing can be written as half, I can take this 2 inside, so that becomes equal to sigma upon square root of 2 omega mu sigma, but square root of omega mu sigma, that is nothing but mod of gamma. So, this is mod E naught square. So, I have here this is equal to half sigma upon root 2 into mod gamma into mod E naught square. And this quantity sigma upon gamma, if I go back to my surface current density, this quantity is nothing but the surface current, that is what we have derived. So, this quantity here, this sigma upon gamma times E naught, that quantity is nothing but the surface current. So, what we can get from here, that this quantity, if I write down appropriately in terms of the surface current density, I will get the power loss, which can be written as from here power loss W, that will be equal to 1 upon 2 sigma upon 2 alpha into mod gamma square upon sigma square into Js square. And if I substitute for gamma appropriately as we did in terms of the intrinsic impedance, this thing can also be written now as mod Js square half multiply by the quantity omega mu divided by 2 sigma. And this quantity, if I go back to the characteristic impedance which I have defined, then I get this quantity from here. The characteristic impedance or the intrinsic impedance of the medium or the surface impedance which we have got is square root of j omega mu divided by sigma, which is same as square root of omega mu by 2 sigma plus j square root omega mu by 2 sigma. So, the surface impedance I can say has a resistive part which I call as surface resistance and a reactive part which I call as surface reactance. So, this one, let us say we write as surface resistance plus some reactance which is the surface reactance. Now, this quantity which we have got here is nothing but omega mu upon 2 sigma, which is same as this. So, we can write this as equal to half mod Js square into the surface resistance. This is a very important result now, that the power loss per unit area of the conducting surface can be obtained by this expression. That means, if I know the surface current density for this conducting boundary and if I know the surface resistance, then the power loss can be calculated as half the linear surface current density square multiplied by the surface resistance. So, later on we will see when we go to the structures like waveguides or something like that, then the conductor loss is calculated from the surface current density, because surface current density we can obtain from the magnetic fields. So, if I know the tangential component of the magnetic field on the surface of the conductor, I can find out using the relation n cross h the linear surface current density, and once I know the surface current density and if I know the surface impedance, then from there I can find out what is the power loss per unit area of the conductor. So, this concept or this calculation of power loss using the surface impedance or surface resistance and the linear current density is extremely useful in calculating the power losses in the conducting media. Of course, here we have calculated the power loss by using the essentially the circuit concept. What I mean by that is, I found out the current, I found out the resistance in the slab, then we found out the I square R loss, and then we got the total power loss which was under the surface of the conductor. We can find the same thing by an alternative approach, and that is by the wave approach. What we argue is that if there was an electric and magnetic field which was on the surface of a conductor, so we have electric field and we have a magnetic field, and once we have electric and magnetic field, they are essentially having a wave phenomena which is going in z direction. So, the power which is going with this wave inside the conductor, that is the one which essentially is lost in these ohmic losses of the conductor, because the medium is infinite and this power is decreasing as the wave travels, no power is coming back. So, I can say equivalently whatever was the power flow inside the conductor, that is a measure of what is the loss inside the conductor. So, instead of doing the calculation of the power loss from this electrical point of view, like finding out the current and the resistance, I can use the wave concept and find what is the power loss inside the conductor. So, if this is your interface and if the electric field in this direction we saw is E0, then the magnetic field is H0 and the wave is travelling in this direction, this is Z direction. I can find out what is the power flow at this location. Since I am asking for a power flow per unit area of the surface, essentially I want to know what is the Poynting vector on the surface of the conductor, and that is the power which is essentially going inside the conductor. So, it will be lost in the heating of the conductor, which is the ohmic loss. So, from the Poynting vector, the P, if I calculate, that will be E cross H. E and H are perpendicular to each other, and this is in x direction, this is in y direction. So, essentially you get E0 H0 conjugate in the z direction. I can substitute for H0, which is H0 for this medium is E0 upon eta c. So, this is equal to your E0 mod E0 square upon eta c conjugate. If I substitute now for eta c and rationalize it, I essentially get the power flow P, that is equal to, or we use the here RMS value. So, we have an average power which is half E cross H. So, let us put factor of 2 here. So, the P will be half, and if I rationalize this quantity eta c, which is square root of j omega mu upon sigma, then I will get this half E naught square into square root of 2 upon omega mu sigma. So, this expression is exactly same as what we have got from our surface impedance calculation, the power loss. So, essentially we can calculate the power loss either by using the concept, the circuit concept, like find the conduction current density, then you find out the ohmic loss, which is I square R loss, or you can use the wave concept to find out what is the power going inside the surface of the conductor, and that power essentially should get lost inside the conductor, because the field at z tends to infinity essentially goes to 0. That means there is no power flow at z equal to infinity. So, whatever power has gone inside the conductor must have been lost in the heating of the conductor. So, either by using wave concept or by using the electrical circuit concept, we can calculate the power loss per unit area of the conductor. The interesting thing to note, however, now is that the power which is getting lost inside the conductor is inversely proportional to the conductivity. That means as the conductivity becomes larger, and the same thing is true for frequency, as the frequency becomes larger, the power flow inside the conductor reduces. And when you go to very high frequency or you go to ideal conductor, which is sigma equal to infinity, then the power will go identically to 0. That means for an ideal conductor, there is no power going inside the conductor. Similarly, when the frequency becomes large, there is no power which is going inside the conductor. What that means is, for higher conductivity or higher frequency, the wave essentially finds a resistance penetrating the conductor. The power does not go inside. So, the fields are dying exponentially very rapidly inside the conductor, and we had taken an analogy. This case is very similar to lossy transmission line. However, now there is a difference, that in lossy transmission line the power was getting lost in the heating of the line. However, in this case the fields are dying down very rapidly, but the power is not lost in the ohmic loss. In fact, the power is not able to penetrate this layer. So, as the conductivity becomes equal to infinity, whatever power you try to put on the conductor, no power penetrates the conductor. In fact, the entire power will be reflected from this boundary, which is the conducting boundary. So, when we go to the media interfaces and the behavior of waves on the media interfaces, that time we will use this concept that whenever we have the difficulty in penetration of the boundaries, the energy will be reflected, and then in the medium from where the energy is coming, you have the wave which is incident on the boundary and the wave which gets reflected because it finds difficulty in penetration of the boundary. So, the circuit concept or the wave concept both can be used for calculating the power loss in the conductor, and we conclude a very important conclusion that when the conductivity is infinite, the wave just does not penetrate the medium, there is no power loss, and the entire energy which is incident on the interface is reflected from the boundary.